always increasing. So what does that exactly mean, right? We know that when we do an open system process, we're supposed to first draw control volume. Then we're supposed to ask ourselves, well, what happens to the mass, right? And we need to know what happens to the mass because the mass carries energy with it. So we can't really conserve energy without understanding what happens to the mass. But then if we're designing something, if we're not watching a process take place with our own eyes, we kind of have to figure out if the process can actually happen, right? And we did kind of this thought experiment last class where we talked about, we can take conservation of energy says that we can burn these logs, but that we can also get the logs back if we just add the mass and energy back in. But that's not true, right? So the universe tells us certain processes naturally move in one direction, and that's the direction of entropy generation. So the entropy in the universe is always increasing. So if we want to figure out if a process is possible, we can do a second law analysis on this control volume to see if the entropy generation rate is positive. Now, we have a rate equation for an open system. We call this the second law, right? And we see that the rate of change in entropy in the system is equal to this heat transfer term plus all the entropy that comes in with the mass minus all the entropy that goes out with the mass plus this entropy generation term. And it's the entropy generation term that we're interested in here. So it's interesting because if we said that entropy is always increasing, you might think that this ds by dt term always needs to be positive. But this term tells us about how much entropy is stored inside our control volume. It's not talking about all the entropy in the universe, right? So this sigma dot term, this is talking about how much entropy is generated by the process that we're doing. We know that real processes that can actually happen, have a positive entropy generation rate, that the amount of entropy in the universe is always increasing for each one of these energy transactions that we're doing. It's like the universe is a bank and there's a transaction fee on every one of these energy transfers. We know that we can't quite get to this ideal case where entropy generation is zero, but that's kind of like the limit of what we could achieve. We might be able to asymptotically approach that state if we could almost get rid of all the irreversibilities or all the loss terms. And we also know that if the entropy generation rate is less than zero, if we're destroying entropy in the universe, then that means we must have done something wrong. We violated the second law, and we're looking at a process that isn't possible in the universe that we live in. So, last class, we showed how we could do first law analyses on turbines and on pumps, and they're pretty nice because turbines and pumps are typically, will often assume that they're adiabatic. And if they're adiabatic, that means I can get rid of this heat transfer term. And in my opinion, when we're doing these second law analyses, it's the heat transfer term that people mess up. So first you got to get the sign of the heat transfer right. So this is the same sign for heat transfer that you'll get if you do a first law analysis. Then you got to pick the right temperature, and we'll talk about that, how we don't pick the temperature inside our control volume. Ideally, we pick the temperature on the boundary, but failing that, we'll take a temperature of the surroundings, the temperature outside the control volume. But you might also notice here that this is a single temperature. It's not a temperature difference. And anytime you see that, the hair on the back of your neck should stand up, and you should think, oh, this is not a temperature difference, so it matters if I pick an absolute temperature or a relative temperature. And it means anytime you have a case like this, you're supposed to pick the absolute temperature, a temperature scale where zero is absolute zero. So Kelvin or Rankine. So this is important when we start to talk about condensers or when we talk about boilers. Now, if you remember last class, I think I told the story about my brother when I was sort of talking about being a little bit apprehensive talking about the second law, but I know for sure that entropy always increases. right? But we can see on this diagram, this condensation reaction, right? So we're staying at a constant pressure. We've gone from something that's saturated vapor, right? So this is all steam, there's no liquid, to saturated liquid. Now, the cool thing about drawing this on a TS diagram, right, is that we can see what's going on with the entropy in the fluid. So as I'm moving down from saturated vapor to saturated liquid, as the quality of my material is going down, I can see pretty clearly from this picture that the entropy in the fluid is decreasing. But how can that be if the entropy in the universe is increasing? So it means that this process, which has a heat transfer component to it, this heat transfer that's coming out of my fluid as my steam is cooling down into liquid, it must be generating some kind of an increase in entropy that's bigger than the reduction in entropy from the steam as it goes to liquid. So we're going to do this. We're going to do an analysis on a condenser to kind of show that this is the case, right? So we know, probably we know, right? You've probably seen condensation happen in real life. Maybe, maybe you're boiling some noodles for macaroni and cheese and you see some condensation happen on the inside of the lid, right? Because the lid is colder, so the steam comes up and it hits the lid, and then you get water droplets that form on the inside of that lid, right? So that's condensation. We know that can happen in the universe. So let's see if it passes the second law, right? So here we have water, or we have steam, right? Which is coming into our condenser, and it exits at liquid water. The pressure at both states 3 and 4 is 0.1 megapascals, or 1 bar. The quality, when we go into the condenser, is 1. So we have saturated vapor, but it leaves at a quality of 0, saturated liquid. So the first thing that we need to do to solve the second law equation is we know that we have a heat transfer term in there. So the first thing we need to do is we need to find the heat transfer rate for this process. So after we draw our, I guess the first thing we want to do is draw the control volume, right? So our control volume is going to be only now this water side of our heat exchanger. So we're going to have this water flowing through it comes in as steam, goes out as liquid, and rejects a bunch of heat because it's cooling down. So now I want to find the symbolic solution for the heat transfer rate here. First, I do conservation of mass. Now, this is kind of trivial, and probably you could do this in your head. But if we say that the system is at steady state, and it's only got one inlet and one outlet, so that's the case that we have here, what conservation of mass is going to tell us is that the mass flow rate in to the condenser is equal to the mass flow rate out of the condenser. So instead of calling it mass flow rate in and mass flow rate out, I'm just going to call it m dot. There's only one mass flow rate in this problem. Now I'm going to move to my first law. I've already assumed that we're at steady state and that we have one inlet and one outlet. I'm further going to assume that there's no work going on inside my control volume. There's no fan that's fan blades that are spinning to drive this flow, and we're not sort of harnessing energy like we would in a turbine. So we're going to get rid of this power term. We're going to say that the change in potential energy is negligible, and that the change in kinetic energy is negligible. And what we're going to be left with is an equation that hopefully we're starting to get a little bit familiar with, that the heat transfer in this case, which is a pretty common case, Q dot, the heat transfer rate, is going to be m dot times HO minus H in, right? So if we were calculating for power, we'd get that high ho, right? We could remember because the dwarves work really hard. So for power terms, we get H in minus H out. For heat transfer rate, if we can make all of these same assumptions, we'll get that Q dot is equal to m dot times H out minus H in. In this case, I know the mass flow rate, but I don't know H out, and I don't know H in, and of course, I don't know the heat transfer rate because that's the thing that I'm trying to find. So what do? This happens all the time in thermodynamics. My argument when you're doing a test is try never to leave it blank, because to get to this point, right, what we needed to do was write down some fundamental equations like the first law, make some assumptions, and then we'll get the symbolic solution. So maybe you've heard of this idea of the 80-20 principle, where a lot of times you get 80% of the benefit from doing 20% of the work. I think that's true in this case. I think the symbolic solution, to get to the symbolic solution, typically doesn't take a whole lot of time, right? You need to understand what's going on, but going through the symbolic solution, it does demonstrate, it gives you a chance to demonstrate that you understand how to do these thermodynamic problems. And this would be worth a significant amount of points on a test, right? So even if when we get to the delta H part, if you have trouble how to fix the states, you've at least demonstrated that you know how to use the first law in this case. So I think it's pretty valuable to do this even before we start to fix the states. So now we need to figure out what H out and H in are. Now in this case, we know the pressure and we're given quality at both states. So I know that my condensation process, in this case, if I was sketching it out, because it's condensation, it's close to the vapor dome. We're actually cutting right across the vapor dome. We move from this state at saturated vapor down to this state at saturated liquid. So first we'll do this state, the saturated vapor state. We know the pressure in the problem, this is a little tricky too, because the pressure in the problem says it's 0.1 megapascals. But I remember that a megapascal is 1,000 kilopascals, and a bar is 100 kilopascals. So 0.1 megapascals is 100 kilopascals, which is the same as 1 bar. So 0.1 megapascals is the same rho here as 1 bar. I want to find H, and because my quality is equal to 1, the specific enthalpy here is Hg. And because I know I'm going to deal with the second law later, I'm also going to write down Sg here for state. I think it's state 2 on my table. So now I put these in. I do a very similar thing with state 3. It's just now I'm on the other side of the vapor dome, so my quality is 0, which means my values are HF and SF. So here I take these values, I write them down, I put them in my state table. So now I feel pretty good because my state table is complete. I can go back to that symbolic solution that I had, and I can put the numbers in and get a value, right? So Q dot is equal to M dot H3 minus H2, H out minus H in. And when I do this, I see that H3, right, this is at the end of the process, this is the liquid state, has less enthalpy than the vapor state. That's what I expect, right? I'm losing heat here, so I expect heat in is positive, so heat out must be negative. I'm expecting to get a negative heat transfer rate, and that's what I get. So I get reasonable units, kilowatts, right, or kilojoules per second, and the sign kind of agrees with my intuition. So I feel pretty confident in this particular answer. So this is good. Now I know Q dot, right? Now I want to see, well, the specific entropy here is decreasing, right? It's going from, just like the enthalpy is decreasing, or the entropy is decreasing as well. I go from 7.36 to 1.30, right? So does that mean that the process is possible or impossible? Because this is the argument that I was, or the discussion, I guess, I was having with my brother, was that just because the specific entropy of the material that you're looking at goes down doesn't mean that the entropy in the universe is going down. So now we want to look at the second law and find that sigma dot, or the entropy generation term. So now we write down our rate equation for the second law. We know that we're at steady state, so we're not storing any entropy in our system. It's one inlet and one outlet. Unfortunately, it's not adiabatic, so I can't get rid of that term. So I'm left now with this expression for sigma dot. I know that the entropy generation rate has something to do with the heat transfer and this temperature of the surroundings, plus m dot times S out minus S in. And I already know that S out is less than S in. So this second part I know is going to be negative. So now I have this expression from the second law. Here's the tricky parts, okay? So the first thing is I got to remember that because I've moved this over to the other side of the equation, this is negative Q dot. So negative 1 times Q dot over T, right? So here, my Q dot term is a negative number. So I have a -1 times a negative number. So this is good, right? That means that this number is going to be positive. I know that this term here is going to be negative. So this is good. I'm hoping that the positive term is bigger than the negative term, because then all this stuff I've been telling you about how sigma dot should be positive, we won't disprove that in this example, right? Now it's important to remember, and this I guess goes back to what we know about the second law. My understanding is we don't get to the second law from first principles. This kind of comes from observation, right? It's empirical. So we don't exactly know that sigma dot should always increase every time. We just know that everything that we've ever seen results in sigma dot increasing, right? So there could be some conditions. Again, I think that book, A Brief Moment in Time by Stephen Hawking, it talks about, well, maybe there's some cases in the universe where time would end up going backwards. So maybe entropy would decrease or something. But I'm an engineer, so I'm interested in practical things. So it's kind of way outside my wheelhouse over there, right? So the one thing is, if people are going to mess up these kind of second law questions, I think they do it on this heat transfer term. The first thing is we got to get the sign of the heat transfer right. The second thing is we got to get the units of the temperature right. So because this is a temperature of the surround, or because this is a temperature that stands alone, it's got to be in Kelvin. Now the other thing is we got to pick the right temperature. So we know that inside our control volume at 1 bar, if we're always under the vapor dome, the temperature is going to be about 100 degrees Celsius, right? But one of the things that I guess I should have talked about a little bit more as we were going through this problem is that it told us that the temperature of the surroundings, right? So it had this thing that said T infinity. So that's the temperature far enough away from our control volume so that it doesn't affect the temperature, right? Because here, so let's say this was just in a room that was at 40 degrees Celsius. So if we got closer to this thing that was 100 degrees Celsius, the air would be affected by the fact that this thing is 100 degrees Celsius. So this T infinity, you'll learn about this more in heat transfer, but this is like the temperature of your reservoir far enough away from the thing that you're thinking about, right? So this is basically just the temperature in the surroundings. So that's the temperature that I want to pick, not the temperature that's inside my control volume, but the temperature that's outside of my control volume, or I guess more, maybe it's better to say the temperature on the boundary of my control volume. But failing that, it's better to pick the temperature outside my control volume than the temperature inside my control volume. So here I picked 40 degrees, but I can't write it down as 40 degrees Celsius because this is not a delta T. So I have to add 273 to get back to Kelvin. So now I've got two terms. This one straight up is in kilowatts per degree Kelvin, right? This one kilograms per second multiplied by kilojoules per kilogram Kelvin. So the kilogram cancels out and I get kilowatts per degree Kelvin. So that's good because my units are the same thing. I'm adding apples to apples here, right? So the good thing here, right, and I think for any process that's going to be possible in the universe, if we do the math right, we'll see that this term here, which is positive, right, 7.214, is bigger than this term here, which is negative, which is negative 6.1. So we've shown that this condensation process doesn't violate the second law. So now we also showed, so we passed conservation of mass if we did the math right. We passed conservation of energy if we did the math right. That's how we found our Q dot, right? And now we've satisfied the second law because entropy generation was positive. So we know that this is a real process. It's not ideal because sigma dot is not 0, but it's not, it doesn't violate the second law because sigma dot is not negative. So this is how we can use the second law when we have that heat transfer term that sticks around. So this is bigger than 0, so we're satisfied. The second law is satisfied that this can happen. So this is one way that we can look at the second law, right? But like many things in science or in life in general, there's more than one way to look at the problem, right? So here we were looking at just the condenser that was strung together in sort of a series of open systems. But if we didn't just look at the condenser, if we looked at the whole system, we would see that here we're going through our turbine, right? So we have some high enthalpy fluid at high pressure. It goes through my turbine, the pressure comes down, so the enthalpy comes down. Now, in this case, I had saturated vapor. What I really want to do, right, because the purpose of this is called a heat engine, right, because we're adding heat and we're getting power out. So really what I'd like to do, the purpose here is to generate more power. So what I want to do is get back to the turbine inlet. So the way that I do that is I take this saturated vapor that's at low pressure. I want to get it back to high pressure, but it's easier to increase the pressure of a liquid than a vapor. It takes less power. That's what I mean by easier. So we remove some heat and that vapor cools down into a liquid. Then we run that liquid through a pump to get the pressure back up. So now it's high pressure, but it's liquid and I want steam. So now this is the part where we maybe have to boil, or we have to burn some fossil fuel to add some heat, right? Or maybe we run a nuclear reaction, right? And that boils that liquid so that we get this high enthalpy steam again to go through the turbine. Each one of these processes is an open system. But because they're aligned together in series here, in total, it's a closed system because all the mass that comes into the boiler goes out the boiler and then it goes into the turbine, right? So this is all closed, right? So this is a closed system. So it's also called a heat engine, right? Because the purpose here is we're adding heat to get work. That's the energy exchange. That's what the name thermodynamics comes from, right? This idea that we can turn heat energy into usable work, right? So this is called a heat engine, right? It's kind of the cornerstone of thermodynamics. So this is a system where we're adding heat and we're getting work. Now, any kind of power plant like this, the power plant is always the first consumer of the power plant because the turbine is producing some power. But in order to keep running the turbine in a cycle like this, right? The idea is this math just keeps going around and around and we keep generating more power, right? But in order for this to happen continuously, we also have to be running the pump. So we think about the net work or the net power, which would be like the turbine power, which is positive, plus the pump power, but the pump power is negative, right? So the net work is going to be something less than the turbine power. This is when the textbook gets a little bit tricky because right around here, up until this point, the textbook has kind of been in line with our idea of heat in is positive and work in is negative. But it doesn't quite tell you this. Right around this point, it starts to say, don't worry, we'll just take everything as an absolute value. So net work in the textbook is turbine power minus pump power. But to do that, you have to make pump power positive. So my suggestion is always going to be work all of these terms out with the first law and add them up. Let the first law worry about what the sign is going to be, right? So here, the purpose of this is we're going to add heat and we're going to get work, right? That's the purpose of a heat engine. So as people started to look at this, they came up with this statement of the second law, right? So there's ways to say these things in words and there's ways to say these things in math. Now, I always prefer the mathematical definition because it makes more sense to me. Like this sentence, which is taken right from the textbook, presumably from Kelvin and Planck, and it's like, it's hard to tell what this means, right? It says, it is impossible to construct a device which operates on a cycle, that means keeps operating continuously for a long time, and produces no other effect than the production of work and the transfer of heat from a single body. So I read this and I basically have no idea what it means, right? So if you're confused when you read this, I'm in good company, right? So the way that the textbook draws these heat engines is kind of as rectangles with circles in the middle, right? This is a machine. So I think if I can't write it out in math, and I don't know, maybe it's because I'm an engineer, right? I prefer, instead of words, to draw a picture, right? So that's what the textbook tries to do, but I still think it's maybe a little confusing just reading the textbook. So what I think this means, or the way that I think about this statement, is that I want an engine, right? Let's think about an automobile engine. The hot reservoir comes, right? The heat source in an internal combustion engine comes from burning the fuel, right? That happens in the pistons. It's pretty hot in there, right? And if I didn't have a way to cool the engine off, I wouldn't be able to, I'd run that engine for a little while, but I wouldn't really think about it as running in a cycle, because what would keep happening is that very quickly over time, the engine would keep heating up, right? Now, I hope this has never happened to you, but sometimes you'll be driving down the road and you'll see somebody on the side of the highway with their hood popped up, waiting for their engine to cool off, right? So that means their cooling system failed. So here, when they say that there's no other effect than the production of work and the transfer of heat from a single body, right? We have to transfer heat in from a hot source to have a heat engine. What this wording is really saying is that for every heat engine, we take some heat in to produce work, but because that engine cannot reject heat back to the hot reservoir, it needs to also communicate with a cold reservoir. Excuse me. So the cold reservoir has to cool down the engine so it doesn't overheat. So in order to have a heat engine, you have to have heat in and you have to have some heat out. Now, this is unfortunate for us because ultimately we'll see what it means is that when we transfer heat in, we can never turn all of that heat into work because we have to reject some of that heat to cool the engine down. So really, this picture doesn't actually work, right? I drew the net work here. There's some heat in, but I also have to draw some heat out. There's always waste heat. If you ever go by a power plant, or if you think about The Simpsons, right? The Simpsons, it's got like a big stack, right? Now that stack is not, there may be some stack where there's some steam, some smoke coming out, right? But the big stacks you see are cooling towers, right? And what's happening is steam is going in there. That's like this condenser, and it has to cool down. So then it goes into that cooling tower, and the steam starts to rise, but as it does, it cools off, turns back into a liquid, and kind of rains down in the tower, right? So we're rejecting heat to the atmosphere. Again, I wouldn't necessarily advise this, but if you ever sort of put your hand in front of the exhaust of your car, you'll notice that the air that's coming out is warmer than the air that's going in, right? That's just the air outside, right? So the air temperature. So the exhaust temperature is higher than the air temperature. But don't get too close to that exhaust. It's not good for you, right? So this is a closed system at steady state if we draw our control volume big enough. So that means we could do a rate equation here, right? So this is just, remember before we had the equation for closed systems as delta T or delta E is equal to Q minus W. Now we've divided by delta T all the terms, right? And taken delta T, the limit as it goes to 0, and we get this dE by dt term is equal to Q dot net minus W dot net. So the net work is the turbine power plus the pump power, but the pump power is negative. And the net heat is going to be the heat in plus the heat out, but that heat out is also negative, right? So there's net heat and net work. And if we're at steady state and we're in a closed system like this, so we have no mass terms, mass flow rate terms, then what we're going to find is that the net heat is equal to the net work, right? So that means that the net work can never be equal to the heat in because we have to reject some heat. It's unfortunate, but that's kind of the price that we pay for turning heat, which we often get from fossil fuels, right? Oh, we're getting it less from fossil fuels, which is good, right? But often we're getting heat from burning fossil fuels, and the price for that is that we don't get all the energy that that we put in with heat, the heat that we get from burning those fuels. So here I can think about the net heat as heat in minus heat out is equal to the net work. And the net work would be the turbine power plus the pump power. Note that I'm kind of doing what the textbook does here, and so these are absolute values, but they're not shown. So this is q dot in is positive, and here q dot out is positive too. So if we wanted to do these both from the first law, this would be q dot in plus q dot out. So now we're going to define a type of efficiency here, right? So if I ever have you for, like if I'm in the audience and you're doing maybe a heat transfer case study, or you're doing your final project, right, your MSD project, then you might say something like, oh, I made this decision because it's more efficient. I will ask you the question, what the heck do you mean by efficiency? Because efficiency has several different definitions in this class, right? And in engineering, this is a specific thing, right? I think colloquially, kind of in common speech, we have this idea that efficiency is kind of a synonym for goodness, right? Oh, something's better, then it's more efficient, right? But efficiency has really got to be some kind of a fraction, right? Something between 0 and 100%, or between 0 and 1, right? So when we look at these whole systems, we're always going to have some characterization parameter that we use to describe how well the system is doing, right? And the way that we do that is we take what's the energy benefit, or the thing that we're trying to get from running our cycle, and divide it by the energy cost. So in a heat engine, the energy benefit is that we're trying to produce this net power. The whole reason that I'm running the series of open systems that we talked about was because really I want to run the turbine. The whole rest of the cycle is just to get me back to the inlet of the turbine. So the energy benefit here is the net power. We're trying to generate power so we can, turn the lights on in whatever room you're in, right? Or your computer is running on power, right? Now the energy cost is not the net heat, right? Because if the energy cost was the net heat, then our efficiency would always be 1. And we'd feel great because we'd be like, oh, sweet, it's 100% efficient every time. Don't even have to do anything, right? But really, the energy cost is the heat that we put into the system, right? So if we were talking about a coal power plant, this would be the heat that we get from burning coal. That's the price that we pay to develop that power, is that we have to burn that fossil fuel, right? So in this case, what we would like to get is we'd like to get our net work as high as it can be while burning as little fossil fuel as we can. And we're going to learn some tricks on how we make things more efficient, where efficiency is, we're talking about this thermal efficiency, right? Now we showed from the first law of that closed system that net heat is equal to net work, and net heat would be q dot in minus q dot out, again, if we take the absolute value of q dot out. And this is going to be 1 minus q dot out divided by q dot in, right? So this makes sense, right? So we have this rejected heat, which has got to be something less than the heat that goes in, right? So I go from 1 minus whatever this is. Ideally, I would like to reject 0 heat, because if I could reject 0 heat, my efficiency would be 100%. But it turns out, right, this is what Kelvin and Planck told us, is that you can't reject 0 heat. There needs to be some kind of a heat sink for you to run an engine in a cycle. So sort of if you get continuous running of a system that's at steady state, you need to have a heat sink, right? So this q dot out is going to be something, right? And it turns out that for thermal efficiencies, we can usually not get close to 100% efficient. Maybe you've heard about this term, but we also sometimes call engines Carnot engines, right? So if you ever hear the word Carnot, it's kind of a synonym for ideal. So if you have an ideal heat engine, we can figure out kind of what the best possible thermal efficiency you could get is, right? And I think because we're used to, sitting for exams and things, and we feel like the best possible efficiency should be 100%, right? And maybe if it would be if there weren't this thing called the second law, right? So for heat engines, the best you can ever do is 1 minus, so So for Carnot engines, what we do is we take these heat transfer terms and we substitute the Q dots for temperatures, right? So this is a ratio of heat transfer rates. I substitute the ratio of heat transfer rates for the ratio of the temperature. So the temperature out divided by the temperature in, right? Now, you see that if you have this temperature in, so you have a combustion temperature of whatever your fuel is, right? And you have a temperature out, which is usually kind of dictated by, maybe it's by the environment, right? You can't really make something colder than the environment, right? So now we know the temperature out minus the temperature in, right? You can make something colder than the environment, but not as the exhaust from a heat engine, right? So this is going to be some dimensionless equation. One doesn't have any units, right? And this temperature ratio is Kelvin divided by Kelvin, right? So the other thing, when you look at this, right, these are not delta T's, so they have to be in Kelvin, right, or in Rankine. So the problem is we're always going to have some finite temperature out and some temperature in that's not going to be infinity, right? So even, but this is kind of neat too, right? Because sometimes, engineers were practical people, right? At least oftentimes. You might look at all these ideal equations and say, like, why would we ever have these equations if no system is ever going to act like this, right? But here we can see pretty easily that if I have a system, here are two things I can do to make my efficiency better. So if I want my efficiency to be better, I want this term to be small. I can make this term small by reducing T out or by increasing T in. A lot of times I'm kind of stuck with the temperature outlet that I get, but I could increase T in if I had some friends that were chemical engineers that could make a fuel that burned hotter, right? Provided that I also knew some materials engineers that could make steel that didn't melt at that higher temperature, right? So just from knowing this equation, I get some idea of how I can make my system better, even if I don't have perfect understanding of how that system works. The other thing that I know is that my ideal thermal efficiency, or the Carnot efficiency, is always going to be better than the actual efficiency, right? So this Carnot efficiency is really the efficiency that I'm chasing given my T out and my T in, right? So it's not that I can ever make efficiency 100%, it's that I can get to whatever the Carnot efficiency is, or at least I could approach that, right? So here's an example of a heat engine where we have a hot temperature of 150 degrees Celsius, a cold temperature of 50 degrees Celsius, and I'm adding heat at a rate of 100 kilowatts. The problem asks me, what's the maximum amount of power that this heat engine could generate? So here, I look at my Carnot efficiency. My Carnot efficiency is 1 minus T cold divided by T hot. Right? So my T cold, that's my cold reservoir. My hot reservoir is over here, right? But these are in degrees Celsius, and I know because these are in temperature differences, I got to turn them back into Kelvin, right? So in this case, the best efficiency that I could ever possibly get is 0.24. So for this 100 kilowatts of heat rate that I'm adding, the net power the most net power that I could ever get is 24 kilowatts, right? So in a sense, I'm losing 76 kilowatts of this heat transfer rate in, right? So obviously, for these things, we'll talk about this a little later, but increasing efficiency is good for everyone because it means that I like living here on Earth, right? I don't have a better alternative at the moment. Right? So, although I don't know, maybe Elon would say that Mars is a viable opportunity, right? But I like living here on Earth. So here on Earth, Evelyn, I can't right now. I'm teaching my class. This is my daughter Evelyn, right? I'll be back in just a second. I gotta take you out of it. Okay. Sorry about that. So, we want to get better efficiency because if we have better efficiency or when we have better efficiency, it means that we get the same amount of power while burning less fuel, right? Burning less fuel means less emissions, right? It also means more efficiency is good because it also means that you end up making more money with whatever process that you're running, right? So sometimes as engineers, we need to be able to speak the language of business. And in the language of business, it's the numbers that have dollar signs in front of them carry a lot of weight, right? So we need to be able to understand how to speak that language too. So we had one statement for these heat engines, right, where we're putting heat in and we're getting work out, right? But there's also this Clausius statement of the second law, and it says, it's another one that's kind of confusing if you just read it, right? So I'll try to explain what I understand it to mean, right? And here it says, it is impossible to construct a device which operates on a cycle. So again, this is like a thing that's running continuously, whose sole effect is the transfer of heat from a cooler body to a hotter body. Now, when you see this, you might say, well, it's actually just impossible to transfer heat from a colder body to a hotter body. And locally, that's true. My old heat transfer professor used to call that the 0th law of thermodynamics, that heat always moves from an area of high temperature to an area of low temperature. But that didn't stop us engineers, right? We're a wily bunch. So what we did was we decided that we could make a machine, right? A machine like a refrigerator or an air conditioner. And this machine has two sides. There's a cold side and there's a hot side. So what happens is the cold side is colder than the place you want to keep cold. So inside of your fridge, maybe it's 4 degrees Celsius. So what we do is we make a machine where on one side it's colder than 4 degrees Celsius. And then we can remove heat from this cold part of your refrigerator, right? Well, that's where you keep your food, right? So heat's coming out of there to maintain this temperature. Now, the consequence of that is that the other side of the machine has to be hot, right? So it tends to be hotter, well, it has to be hotter than the temperature in your room, right? So the fridge, if you ever pull it out, you look on the back, there's those coils, right? And it's kind of hot back there, right? Certainly hotter than room temperature. So we can make a machine that kind of bends the universe to our will a little bit because it makes it look like we're transferring heat from this cold place, my refrigerator, to a hot place, which is room temperature inside my kitchen. Now, the tricky thing here in this statement, the part that's maybe not said so explicitly, is that we can't make something whose sole effect is the transfer of heat from a cooler body to a hotter body. But I think that's pretty ambiguous, right? Both of these statements, I don't really like the wording, right? So what it's telling us is I can't make a machine that transfers heat from a cold place to a hot place, if we zoom out far enough, right? And produces power. I can't even do this and have a machine that I don't have to plug into a wall, right? Instead, the only way for me to make a machine that's really cold on one side and then as a consequence hot on the other side is if I plug it into a wall. If you notice, your refrigerator and your air conditioner, if you have like a window air conditioner or if you have a central air conditioner, this is true too, right? They only work because we run electricity to them, right? They have compressors in them. And those compressors are adding power into the fluid that's running through them, the refrigerant that's running through them. So what this means, this Clausius statement of the second law, what it means is that we can make a machine that looks like it's moving heat from a cold place to a hot place, but only if that machine consumes power. So the price here is that we got to plug it into the wall, right? And there's two types of machines that do this, and really the difference between them only depends on your perspective, right? So one of them is called a heat pump. Depending on where you live, you might have a heat pump instead of a gas furnace in your house to keep it warm, right? So if you're in a heat pump, right, or if you're using a heat pump, as a human, usually the part that you're interested in, your perspective, is from the hot place, So in the heat pump, the energy benefit is the fact that you're adding heat to the place that's hot, right? So if you're using this to heat your house, you want to add heat to your house even though it's colder than your house outside, right? So the heat pump transfers thermal energy from a low temperature place, in this case outside, to a high temperature place inside, right? So it's a heater. The Clausius statement tells us that it's not possible to do this without adding power to this system, right? So now we don't have something called a thermal efficiency for a heat pump. And that's because when we do this, we'll get a value that's bigger than 1. And thermodynamics is not like sports. You can't get more than 100% if you're talking about an efficiency. So instead, we have this thing called a coefficient of performance, right? If you ever have to buy an air conditioner, we just bought an air conditioner last winter, right? We actually bought the furnace, and so we did the air conditioner too. And they talk about a SEER rating, and the SEER rating is related to the coefficient of performance for a refrigerator, right? So coefficient of performance for a heat pipe, you can just write COP, superscript heat pipe, but we use a Greek letter here, this is gamma, that we use for the coefficient of performance for a heat pump. But again, all of these coefficients, right, all of these ways that we're characterizing these different cycles are going to be the energy benefit divided by the energy cost. So for the coefficient of performance for the heat pump, the energy benefit, because we're sitting in the hot place, the energy benefit is the heat transfer that we add to the hot place. And the cost is that we got to plug this thing into the wall, right? So we got to add some heat, or we got to add some power into the system. We know that this net work is also equal to Q dot hot minus Q dot cold. This works for any kind of heat pump, whether it's real or it's ideal, right? But if I want to talk about a Carnot heat pump, or if I want to talk about my maximum possible coefficient of performance given these temperatures, then I can change these ratio of Q dots into a ratio of temperatures. Again, here we have a temperature that stands alone. So on top here, you've got to use Kelvin or Rankine. On the bottom, it doesn't really matter because it's a temperature difference. So you could use either Celsius or Fahrenheit or Kelvin or Rankine. But my advice to you is that whenever you're calculating coefficient of performance, Carnot coefficients of performance, or Carnot efficiencies, it's better to just use Kelvin or Rankine because then you won't mess up. All right, so I would advise you to always use absolute temperatures in these equations. Right, so a Carnot heat pump is an ideal heat pump. It's not real, but maybe looking at this equation maybe tells me how I can get better performance. Right, so it shows us how performance changes with temperature, and it gives us some target that we can shoot for. Right, so what's the theoretical maximum that we could possibly get? Right, the other type of system that we might be interested in if we're using this Clausius statement is a refrigeration unit, right? So in a refrigeration unit, our perspective, right, the thing that we're interested in is how much heat do we reject from the cold place, right? So now, you know, our cold part of our machine is taking heat out of the cold place, and that's the energy benefit that we're interested in, right? So for refrigeration, we're transferring heat from a low temperature area to a high temperature area. And Clausius tells us that we can't do this without adding power, right? So your fridge doesn't spontaneously cool down. You got to plug it into the wall, right? I'm sure that's not a surprise to anyone, right? So now we have a coefficient of performance for a refrigerator. The Greek unit, or the Greek letter we use here, is beta. I try to remember this because a beta looks kind of like an R, or at least it looks more like an R than gamma, right? So beta is the coefficient of performance for a refrigerator, but it's fine for you to say COP superscript R. And this is going to be the desired energy effect divided by the energy cost, because all of these performance metrics are this equation, energy benefit over energy cost. For a refrigerator, the energy benefit is the heat that we're removing from the cold place, and the energy cost is that we got to plug this thing into the wall. So what's the net power, right? The power it consumes minus whatever power it generates, if we're talking about absolute values like the textbook does. If I want to find, right, so I also know from a first law analysis of the whole system, which is a closed system, that the net work, if we're at steady state, is Q dot hot minus Q dot cold. Now again, I have this ratio of heat transfer rates, and I can turn that into a ratio of temperatures if I'm talking about the Carnot coefficient of performance, or the maximum possible coefficient of performance that I can get, right? So just like with the heat pump, we can see that there's a maximum value, and this equation gives us that maximum value. And again, we want to use absolute temperatures, right? Just like with the heat pump, a Carnot refrigerator would be an ideal refrigerator. They're not real, but knowing the equation might give us some hints on how we can improve performance, and it gives us a target that we can shoot for. I guess it's not even realistic, because we know we can never get to that, but we know for sure we can never get past that, right? We can at least, the Carnot efficiency, or the Carnot coefficient of performance, is sort of the limit of what we could ever achieve, given that we don't change the hot temperature and the cold temperature. So that is all that I wanted to talk about today. I'm happy to field any questions that you might have. All right. Well, thank you very much, everyone.